Okay. So last time we implemented this attention layer, and we started to implement attention model, and I copied the code from a notebook that I used for machine learning class, but in that notebook, I used the last output layer from encoder as input to decoder. And I said last time that actually we will initialize the input state for decoder by zeros. So let's fix that part. So let's look at the encoder. And instead of calculating this last state, we will initialize our decoder start by zeros. So this is the first correction to encoder.
Is this in the basic model?
No, it's in attention model.
Okay.
So it's attentive model. So we started to implement encoder, and so in encoder we create embeddings of our input. Then I also will need a batch size to initialize the start of decoder. So then we calculated this. Sorry. First we used embeddings, then we calculated the encoder hidden states. And after that, please comment this line when we calculate the mask, because there is a built-in function that calculates mask. So, and also instead of using the last state, which is not really last from the encoder, we will use just zeros as initial hidden state input to decoder. And then we apply attention layer to our entire encoded sequence, decoder starts, which is 0 in the beginning, and mask. And the mask, which we calculate with this built-in function. So this is, and we return, we return all this decoder start, encoder sequence, mask, first input to attention, because it's encoder, we calculate the first attention, and the vector of the probabilities, where so high probability corresponds to the token with where our attention actually looks at. So and we will implement the following model. Encoder. So we have encoder. So we have embeddings of the input text in French. Then after encoder, we have these outputs, which we refer as encode sequence. So this is encode sequence. Then mask says where was the end of sequence, end of sentence token, as you remember. Then we have decoder. In decoder, this is decoder. In decoder, the first input is the begin of sentence token, which we know. And the hidden input will be just a vector of zeros. So it will be decoder start. You remember in Seq2Seq, we used the output from the encoder as input. Now we will use attention, so we don't need any information because we will look at the entire encoder every time we predict a new token. Start. And as you remember, we should calculate the first decoder output. And then we pass this output through linear layer, which will transform this into size of our dictionary to predict, to get the probabilities of any token in our dictionary. So what we will do next, we will calculate attention with our outputs. So this is the output, this is the hidden vector. So we will calculate attention of between this vector and entire sequence. So this will be attention layer. And then we will use this attention as input to our next recurrent cell. So instead of using just hidden vector, we will use actually hidden vector that looked at all input tokens. So this is the idea. But the first input, which we initialized by zeros, we also will look at our encoder, and this is how we calculate this first attention. So in first attention, we apply attention layer to encoder and decoder start. So, okay, so this is the encoder. So encoder returns the encoded sequence, decoder starts, the vector of zeros, mask of encoder, but also the first vector of attention and probabilities. Again, probabilities we only keep for visualization. You don't need to keep probabilities from attention layer, but if we want later to visualize at every step at which word or words our attention actually looked at, we should keep these probabilities. Now we will go to, so can we move to decoder? Okay. For decoder, I will reuse the code from base model. But so let's look at the base model. So in the base model, in the code, we have this begin of sentence, then the output from the first token in decoder, because it's begin of sentence, we initialize just with one hot encoded vector with one on the place of the begin of sentence. So this is our first output from decoder. Then we initialize a list of all these probabilities. So this is the first vector, but then we will predict next token, we will get next vector. So we create a list, and then we iterate so out tokens. During training, we actually know the translation. So we know actually the length of the output sequence. So that's why here we iterate from 0 to the length of our ground truth. And then we take one word at a time, one token at a time, and apply the code step. And in the code step, actually, we will look at our encoder and apply attention. And from the coder step, we will get the probabilities and so on. So we will keep this in this variable state, and also the vector of logics that we will append to our logic sequence. Yeah, we append this and we return this. In the end, after decoder, we will get the list of the probabilities, and then we will use them in our loss function. So I will just copy paste this decoder step and decode. And then there is decode inference. In inference, we actually don't know the length, and we will just generate new tokens till the maximum length or the end of sequence token. And then there is also code to translate the lines. Okay, so I will just copy this in our. Actually, maybe I can just change the code step and reuse these functions. Let's see, maybe it will work. If not, I will copy the rest. Let's just maybe copy the code step. Maybe we can just reuse all other functions. Okay, so the code step. Oh, let's see, maybe. Oh, I believe it's my decode step. Okay. So in decode step, we will have information from our previous step, which will be a list, and previous token. It should be token, not tokens, because we will generate a new token. So we will look at the previous token, I believe. Okay. So we'll code. As you remember, in previous step, we return these 1, 2, 3, 4 variables. The hidden vector, the entire encode sequence and mask, and also previous attention. So we will read from previous state, we will read all this information now. So I denote this previous decode state. Then we have encode sequence. Then we have mask. Then we have previous attention and probabilities. Previous attention and previous attention probabilities. So this information we will get right after encoder, but also after every iteration in decoder. So next, previous token embeddings. Yes, we calculate the embedding for the token here. Then here we should correct this. Here we calculate a new decoder state. Oh, actually understand new decoder state. So new decoder state. So this is automatically generated text. I just want to double check. It's a decoder. Previous token embeddings and attention. Oh, I'm okay. Sorry, I confused with another architecture. So yeah, I said that we will use hidden as input. No, we will use in this you can do in your homework. We will use just concatenation of the attention vector and the embedding. So, and actually, yeah, this code is correct because we use concatenation of the token, attention, and this will be the input to our LSTM or our GRU cell. And the hidden vector is the previous decoder state. So this code is correct. So I just want to correct our model. So we will use here encoder and attention concatenated. So this attention will go to we will concatenate with embedding of the inputs token. And this is what this line is doing. So let's check the next line that was generated. Output logits. Yeah, this line is correct. And after that, we should calculate a new attention and new probabilities of attention. So we generate a new vector, hidden vector here. And now we need to go back to encoder and calculate attention with encoder for the next token. So now we calculate attention and attention probes, applying our attention layer to the encoder with new decoder state and mask. This looks good. Yeah, this looks good. And finally, we return new decoder state, encoder sequence, mask, attention, attention probes, and logits. Okay, this looks good. So maybe I should repeat again what what we are doing. So we generate the output from a decoder, then we go to encoder, calculate attention with this encode sequence. After that, we use this hidden vector as input to our next cell, and attention as the vector that we use concatenate with input embedding of the word. Does make sense? So the hidden vector we use as input to our next step in our current neural network. Attention we use as input to this cell concatenated with the token of the English word. Does that make sense? And after that, we our LSTM cell will predict a new hidden vector and will repeat this in a for loop. So then, based on this input and this input from below, it will generate a new hidden vector. Does it make sense? Okay, so let's try to run this code and maybe all other functions, the code and translate sequence lines, it will work with as is. Let's try to do that. Oh, actually, I didn't run. Okay. So and this is my just ignore this. This is my previous code, which is also correct, but I just wanted to write with you. So before I switch to GPU, I will copy also the training loop. So we will initialize our model Oh no, sorry. Yep. And we need to copy paste training loop from our Seq2Seq notebook. We will just reuse that code for training loop. Um, I copied blue. Yep. And this training loop that will plot this metrics. Okay, let's now switch to GPU. Load the data. And yeah, hopefully we need only this decodes to change only this decode step. Let's see. If not, I will also copy paste the decode and the rest remaining functions. Okay, let's initialize our model and try to run this code. So if we won't get an error, then we can reuse the decode function from, yeah, it works great. So, and you can see that loss goes down and this metric blue goes up. And if you compare this with our Seq2Seq model, the blue here, the highest value was about 25. In this case, it should be about 50 with attention. And yeah, actually I have pre-trained models. I can just upload my pre-trained model in the interest of GPU time. um, just to show you the result. What's models? So I will upload the weights. Oh, wait a second. Why model is the weight? Okay, I'm sorry. There was a mistake because I don't want to use a base model. It should be our okay, just comment this line. Yeah, it should be our model. Okay. Let's train it again. Yeah, so you can see that blue goes up much faster than in Seq2Seq model. Sorry, for some reason I didn't notice that there was base model. Okay, and yeah, you can see that it goes kind of much faster up the metric. And now let's upload pre-trained model. So model state dictionary um, from yeah. Mm, what is the syntax? Load state dictionary. Load state dictionary. Aha. And also we need torch load. Okay. Torch dot load. Now our model will have pre-trained weights, and we can use it for evaluation. So let's copy paste this code where we just print the translations. Okay, and here are the translations. And as you remember, in Seq2Seq model, the first phrase was translated. David is a specialist in French, but I believe it's incorrect translation. So now with attention model, it looks much better. Take a seat instead of what was that? Go back. So yeah, this is then you can visualize this attention. So that's why we actually stored these probes. And to visualize, I just provided the code for you. Um, so um, we read some data and from developing set or from validation set, and we store the probabilities in our states. So then you take the last element from the state. As you remember, the last element was actually attention probus. And you can visualize this attention. Let's take a look at the attention probus. So because our attention was used like before translation producing the new token, so here we have begin of sentence, and our attention looks actually at the next word. So begin of sentence looks at the friend, and then it translates it as take. Then take will look at the well, actually, it's hard to say because it looks at all these tokens, but with higher attention to the place, and it translates air. Then air also looks at all these tokens, and it produces sit. Does it make sense? So next sentence. Oh, actually, I should stop running GPU to save it. 1 second. Time. So next example, and I can begin of sentence looks at these three tokens, and the highest probability L, so it translates she. Then when we translated she, we use this she here, but also we go to encoder, and attention from she looks at these tokens, nef, pa, and translates this doesn't. Then apostrophe, then. So this is how it works. And you can see that in some cases, like in this example, for example, for this phrase don't, it looks at different places in the input sentence. This, who, and pa, and in French, pa corresponds to the negation. Yeah. So this is how attention works in practice. Does it make sense? Okay, I'm happy that we finally implemented Seq2Seq with attention, and your homework will be to play with to build two other models. For example, instead of concatenating attention in the input to our cell, you can concatenate attention in the output before. So one of the possible models is instead of using attention here, you can use attention here. You can concatenate attention here before applying linear layer, which calculates logits, and you can compare the performance and by blue score. Another option is to use attention as the hidden vector as input. Another option is to use, instead of LSTM, bidirectional LSTM, as in the first attention architecture in Bogdanov attention. So you can just build two different from my attention architectures, and this will be your next homework. And by the way, we will extend this homework by 1 week, not by this Monday. So you have more time to understand the code and to build your models. Okay, so that's it for today. And on next time, Friday, we will talk about transformers. And next week, we will talk about BERT, the first large language model.